In this video, we will learn about the water ionization constant Kw and equations for calculating pH, pOH from hydronium ion concentration and hydroxide ion concentration. So we said earlier that water can act as both an acid and a base. So let's see what happens when we put water in a reaction with itself. So water is amphoteric, and so water can react with other water molecules in order to produce, if that is an acid and that is a base, the acid will give up a proton and become OH minus, and the base will accept that proton to form H3O plus. And so since water is amphoteric, then it can act as either an acid or a base. And so neutral water will contain both OH minus ions and H3O plus ions. The amount of OH minus ions and the amount of H3O plus ions is very small. So the molarity of OH minus in solution is 1 times 10 to the minus 7th molar. So that's very tiny. And the molarity of H3O plus is also 1 times 10 to the minus 7th. So these two amounts are equal to one another at 25 degrees Celsius. And so even neutral water has some H3O plus ions and some hydroxide ions. Now what's really interesting is that the molarity of H3O plus times the molarity of OH minus is a constant. And so remember we said on the previous slide that each of these was 1 times 10 to the minus 7th. You see how they're 1 times 10 to the minus 7th? And so if you have 1 times 10 to the minus 7th, and then 1 times 10 to the minus 7th, then that is equal to 1 times 10 to the minus 14. And this is a constant. No matter what H3O plus is or what OH minus is, this number is constant. And so if we add an acid and increase this value, then this value is going to drop in order to maintain this value, because this is a constant. There's always this relationship between the molarities of hydronium and the molarities of hydroxide. We will learn more about this when we do our next chapter on equilibrium. But this constant is also known as Kw, or the ion product constant of water. So the K stands for ion product constant, and the W afterwards stands for water. Now, although this is a molarity and that's a molarity, this Kw value has no unit for simplicity by convention. So in neutral water, the H3O plus and the hydroxide ion concentrations were equal, and they were 10 to the minus 7th power. If you add an acid to water, acids donate protons to water, which would increase the H3O plus concentration. So if you increase the H3O plus concentration in water, then your hydroxide ion concentration is going to be more than 1 times 10 to the minus 7th molar. Now, since Kw is a constant, your hydroxide ion concentration would drop to be below 1 times 10 to the minus 7th. And then we classify this solution as being acidic. So when we add an acid, it's acidic. And we have a higher concentration of H3O plus. In a base, we have the opposite situation happening. Bases increase the hydroxide ion concentration. And so in a hydroxide if you increase the hydroxide ion concentration, then it's going to go above 1 times 10 to the minus 7th molar. Now, since Kw is still constant, then that means that the hydronium ion concentration has to decrease. So adding a base makes a solution basic. So here's a practice problem for you. It reads, what is the hydronium ion concentration if the hydroxide ion concentration is 5.0 times 10 to the minus 8th power molar? Go ahead and pause the video and try to work this out on your own. Okay, let's go over this. So we have Kw is equal to my hydronium ion concentration times my hydroxide ion concentration, and those two things have to multiply together to be 1, I'm going to write 1.0, 1.0 times 10 to the minus 14th power. I am told the molarity of this, and I need to find my H3O+. And so this is what I'm solving for. These two things are multiplied together. So if I'm trying to isolate the H3O+ on one side of the equation, I have to divide both sides by OH-. And so that tells me that my H3O+ concentration will be equal to 1.0 times 10 to the minus 14th divided by 5.0 times 10 to the minus 8th molar. I'll go ahead and, no, I'm not going to write a unit yet. And so when I do that in my calculator, I have to make sure that I communicate with my calculator the scientific notation and make sure that I'm communicating with my calculator that the denominator is 5 times 10 to the minus 8th power. And my calculator gives me a really, really tiny value. My calculator likes to max out the display. And so I see 1, 2, 3, 4, 5, 6, and then a 2. 1, 2, 3, 4, 5, 6. Yep. So most calculators only have an 8-digit display, including the decimal points. That's 1, 2, 3, 4, 5, 6, 7, 8. So anyway, force your calculator into scientific notation. So I'm going to go up to mode on my calculator and forcibly change the mode from normal to scientific. Now when I go back and do that, it tells me that my concentration is 2 times 10 to the minus 7th. But I have to consider sig figs. This is 2 sig figs. And so I need to write 2.0 times 10 to the minus 7th. And then I have to remember that this is a molarity. And that molarities have units of molarity. You want to force your calculator into scientific notation because sometimes your calculator rounds in order to show you that one digit that it has room for. But by forcing it into scientific notation, you'll know whether it was a rounded number that you were seeing or if that was actually the value. So I didn't know what these other digits were, and so sometimes it would round away. Okay, so that's my answer to the question. Okay, so we have this balance happening between the hydronium ion concentration and the hydroxide ion concentration. And so I'm lazy sometimes, and instead of writing H3O+, then I write H plus. It's a little bit faster. But know that based on our Bronsted-Lowry definition of acids and bases, that H plus would connect to a water and be H3O plus. I'm just lazy. But the important thing I want you to get from this slide is that even if you have a really acidic solution and we have a very large quantity of H3O plus ions, then we're just going to have a very small amount of OH minus. It's never a zero amount. It's just a very, very tiny amount. And similarly, in a highly basic solution, the amount of hydroxide ion is very small, but it's not zero. And so these are not to scale. Notice how those are like 10 to the minus whatever powers. And so sometimes we kind of want to talk about things where it's not written in scientific notation. And so that's why scientists have invented this pH scale. The concentration scales are huge, like 10 to the minus whatever power. So we want to simplify things, and so we're going to switch to a logarithmic scale, which is pH. And so we can see that here we have our H3O plus, and this says pH. Our pH will be equal to the negative logarithm base 10 of our H3O plus concentration. Now, if I want to solve for my H3O plus concentration, and I'm given pH, let's inverse this equation. So let's do a nice review of logs. And so if pH is equal to the negative log of H3O plus, so we have to think about what's the inverse operation of this logarithm if we want to isolate this. Let's try to solve for this. So I can move this negative side to the other side of the equation by multiplying both sides by -1. But then this logarithm, to undo a logarithm, we have to raise both sides to 10 to that power. And so 10 to the minus pH is equal to, that's a log base 10. So the log will cancel out, and then I'll be left with my H3O plus. So on Alex, there's a log review assignment for you to help you remember the properties of logarithms and how those work. So if you're given pH, you can solve for your H3O plus concentration. Or if you're given the H3O plus concentration, you can solve for pH. So our pH unit, we have to remember that those are 1 apart, but a difference of 1 in pH means a 10 times difference in acidity. So our pH range is usually between 0 and 14. That's the range that we're looking for. That's our typical range. We'll pretty much stay within that. There are some exceptions if you go searching on the internet, but we'll be sticking within the range of 0 to 14. The pH of pure water is 7. And that, remember, if we had our in neutral water, that was our hydronium ion concentration, was 1 times 10 to the minus 7th. And so that gives us a 7 pH. POH is analogous to pH, but for the hydroxide ion concentration. And so POH would be equal to the negative log of my hydroxide ion concentration. And I can do the same math that I did before in order to solve for my hydroxide ion concentration. If I'm trying to do the inverse, I can solve for my hydroxide ion concentration by doing 10 to the negative pH exponent. POH, POH, POH. Caught myself. Okay, and so this introduces a new significant figure rule. So far in this semester, we have only done 2 rules for significant figures. We did 1 rule for multiplication and division, and we did a different rule for addition and subtraction. Now we're going to be using a 3rd significant figure rule. This one we only use when we're doing pH calculations, because this is the only chapter in which we encounter logarithms. And so that's why I'm only telling you about it now. It's because we only need it for this chapter. So how this calculation, the significant figure rule works, I'm going to be teaching it to you in the context of the molarities. So we have to look at this coefficient that goes into our pH. And so we have to remember that our pH is equal to our negative log of the hydroxide ion concentration. And so if this concentration has 2 sig figs, then in this pH calculation, we're going to have 2 after the decimal point. If we had 1 significant figure go into that logarithm, then you're going to have 1 after the decimal come out. Now, the trouble is once you go the other direction. So you have to know that if you have pH, you have to look at the digits behind the decimal point, and then when you inverse it and go backwards, you'll know how many are in your coefficient. So you have to pay attention to what you're looking at and how you're counting your sig figs here. But no matter what, this digit in front of the decimal point does not count towards your significant figures. It's these afterwards that we're caring about. Now, as for calculations for this chapter, we have mentioned H3O+, we have mentioned OH-, and we talked about how pH is the negative log of H3O+, and POH is the negative log of OH-. The hydroxide ion concentration and the hydronium ion concentration are related by that Kw equation. And so you should probably copy down this square and the equations into your notes. You can pause the video in order to copy this page down into your notes. This is a solution map to help you with the calculations. We'll have to think about which corners are we on and which corner are we trying to get to. Then we'll be able to pick our pathway around the square and apply the correct equations. Here's an example problem. This problem says calculate the pH of a 0.0010 molar barium hydroxide solution and determine if it's acidic, basic, or neutral. Before we calculate, let's make a prediction about what we think it will be. Do we think it will be acidic, basic, or neutral based on the chemical formula? Go ahead and pause the video and try to predict whether this compound, barium hydroxide, will make an acidic, basic, or neutral solution. If you picked basic, you were right. This is hydroxide. And so we think it will be basic. Let's verify it mathematically though. So let's write an equation for barium hydroxide in water. So if we have barium hydroxide and we react it with water, our barium ion is just a spectator. It's not going to do anything. And then the OH minus here will act as a base and grab a proton from water to produce H2O. And then the H2O will turn into hydroxide ions once it loses that proton. So now let's balance our equation. I see 2 hydroxide ions here and only 1 over here. So I'm going to add a 2 coefficient there. Add some state symbols if you like. So what I need to know is I need to know my molarity of OH minus. That's going to be the easiest thing to find. So my molarity of OH minus will be equal to my molarity of barium hydroxide. I'm going to rewrite that as moles per liter. Barium hydroxide. I need to cancel out my moles of barium hydroxide. And I need to get moles of OH minus. There will be 2 moles of OH minus for every 1 barium hydroxide. And so my molarity of OH minus will be 0.0020 molar. Now I know my OH minus ion concentration, and so I have a choice. I have this value, and it's my choice whether to go down and then across, or whether to go across and then down. You have 2 options. I'm going to go down and then across. So I need to use this equation right here in order to find my POH. Go to the next slide. So my POH will be equal to the negative log of my hydroxide ion concentration, which is equal to the negative log of 0.0020. Now, if you have the TI-36X Pro, then you have to push the log button twice. Pushing it once gives you the natural log button, but you want the regular log base 10, and so you just have to push it a second time to get log base 10. So do negative log of 0.0020, and so you should end up with 2.69897. And then that's my POH. Now, based on my significant figure rule, I have 2 significant figures going into the logarithm. And so once that comes out, I'm going to have 2 significant figures after the decimal point. I'm not going to round yet because I'm not done with the problem. We are asked to find pH. POH plus pH is equal to 14. So I need to subtract POH from both sides. And so pH will be equal to 14 minus my POH. And so that is 14 minus 2.69897. which is 11.301. And so based on the subtraction rule, this was significant to the hundredths place, and so this needs to be significant to the hundredths place. And so I will report my answer as 11.30 is my pH. pHs that are greater than 7 are basic. And so since 11.3 is more than 7, my solution is basic, just like we predicted. Now, if you go through the PowerPoint on your own, the other pathway around the square is presented, but we end up with the same answer in the end. Here's a practice problem for you. It reads, calculate the concentration of the hydronium ion for a solution with pH 3.7. Go ahead and pause the video and see if you can work that out. Okay, let's go over this. And so pH is equal to the negative log of my hydronium ion concentration. Now I'm trying to solve for that. So I'm going to move the negative sign to the other side of the equation by multiplying both sides by -1. And now I need to isolate my H3O plus by doing the inverse operation to my logarithm. The inverse operation is 10 to the power. And so 10 to the power of negative pH is 10 to the negative power of pH. And my 10 to the power of log base 10 cancels out, and then I'm left with H3O plus. So my H3O plus will be equal to 10 to the negative 3.7 power. So let's do that. 10 to the minus 3.7 is equal to 0.000199526. And now I'm looking for a molarity, and so I need to remember to put my unit. And as far as significant figures goes, there's 1 behind the decimal in my pH. And so that means I need to round this so that there's 1 significant figure in the molarity. So I need to round up, and so that will be 0.0002 molar. You can also do a prediction to make sure that you're calculating things right. So remember, 10 to the minus third is equal to 0.00123. And 10 to the minus fourth is equal to 0.0001. And so if we are doing 10 to the minus 3.7, we expect our number to be between those two numerical values, but closer to the bottom number. And our number is